If you're on a surface at a point and you begin walking in some direction, what's going to happen? Well, it depends on the surface and it depends on the direction that you walk in. Are you going to go up the hill? Are you going to go down the hill? What is the rate of change of the surface if you take a small step in one direction? We name this object the directional derivative. Let's suppose that z is a function of x and y, so this graph should be a surface in three-dimensional space. And we're standing above some point in the xy plane, x naught, y naught. We're going to take a very small step. And the question is, what happens to the surface? Does it go up? Does it go down? So the answer depends on which direction that you walk in. You know, if we walk in this direction, maybe we're going to go up the hill. If we walk in this direction, maybe we're just going to go across the hill and the rate of change would be 0. So the goal is, given a direction, if we take a small step in that direction, what happens to the height of the surface? So these are the tools that we're going to need from previous lessons. So the first one is partial derivatives. So f sub x is going to be the rate of change of the function if we walk in the direction parallel to the x-axis. And likewise, f sub y is going to be the rate of change of the function if we walk in the direction parallel to the y-axis. Also, we learned about the chain rule. Here, if you want to calculate dz dt, you've got to draw one of these cool dependency diagrams and then multiply along the paths and add up all the paths. Then we came to this really cool realization that this is actually a dot product. It's the dot product of the vectors del z del x del z del y dot product with dx dt, or I messed this up, this should be dx dt, dx dt, dy dt. You know, if this isn't immediately obvious to you, pause the video and take a minute to check this math. And I'm just going to mention this. This thing right here has a name. It's called the gradient. And the symbol that we use for this is del z. So we can use these tools to answer this question: how does the height of the surface change if we move in the direction of u? So we're going to start by taking the direction that we want to move in and finding a parameterization for that line. Now, you need to make sure that whatever parameterization you choose has the particle moving along the line at speed 1. So our parameterization, the direction needs to be a unit vector. Otherwise, when we take a small step, like let's suppose that we parameterize the line and the particle is moving along the line very quickly, then if we take a small step in this direction, actually, because the parameterization is moving along the line, that will actually turn it into a really, really big step. And then that's going to make the rate of change of the surface look even larger. So we don't want the rate of change of the surface to depend on the parameterization we use. So you always have to make sure that you use a unit vector to represent the direction of motion. All right, we're ready to do it. Let's go. I've made one up here. I've given us a surface, y minus x cubed. So we're somewhere on that surface above the point 1, 2 in the xy plane. And we're going to try to walk in this direction, 4, 3. So let's hop over to CalcPlot 3D so we can have the visual here. So this is the surface. It's kind of pretty. Green and magenta color theme. It's got a nice little sort of fold in it. It's kind of pretty. All right, so where are we at? Okay, so where we're at is that blue dot right there. That's where we're at. All right, that's above the point 1, 2 in the xy plane. Okay. All right, so let's look just in the xy plane. All right, so we're at the point 1, 2, and we're going to walk in that direction. Okay, that's the direction in the xy plane that we're going to move in from the point 1, 2. You can see it's over 1 up 2. That's where we're at, and we're going to walk in that direction. That's the direction 4, 3. Okay, so back to 3D. All right, so there's the surface, and there's the point, and that's the direction that we're going to walk in. So I think from this visual, you should at least be able to predict if the answer is positive or negative. Just looking at this, just giving you a chance to think here. I think that if we were at that blue dot and we walked in the direction of the little black line right there, I think we should move down the surface. And just to show you that this does depend on the direction, if I change the direction that we're walking in, I think now if we walked in this direction, can you see how if we walked in that direction, I believe we would be moving up the hill. Okay, so by what amount? I mean, I think we should get a pretty large negative number here. I mean, it looks to me if we walk in that direction, if we took a small step, we would go down quite a bit. So let's do the math and crunch out the answers and see how it comes out. Okay, so the next thing that we need to do is find a parameterization of the line. So this is just kind of previous material. I think everybody's familiar with this. I already wagged my finger at you about making sure that you use a unit vector for the direction. So the first thing I did was I found the magnitude of u. I got 5. And then I rescaled u to make it a unit vector. I just divided by those magnitudes. And then, so this is the direction that it's moving in, and it's moving from the point 1, 2. So that's where I got this 1, 2 right there. And that gave us the parameterization of the line. I'm just trying to use this formula right there. So now what I need to do is get these dx dt's and dy dt's, dz dx's, del z del x's, and del z del y's. Okay, so there's my surface. Remember, calculating partial derivatives is easy. For del z del x, I'm just going to pretend that y is constant. So I get negative 3x squared, and for del z del y, I'm just going to get 1. But we actually care about these partial derivatives at the point 1, 2 there. So at 1, 2, del z del x is just going to be, so I'm just plugging in the 1 right there, is going to be negative 3. And del z del y, well, it's just a constant. It's always 1. All right, now I'm trying to use this formula right there, and I think that this is going to kind of sort of take the pressure off us a little bit, because I did this and I kind of just flew through it, because really you don't need that full step. You don't need to write the full parameterization of the line. In order to use this formula, all you need is dx dt and dy dt. So dx dt, all right, so here's x. So dx dt is just 4/5, and dy dt is just 3/5. So you can see that, like, we have a lot of complicated symbols, dx dt, dy dt, but that information was already there just right from the very beginning about it's just the unit vector in the direction. All right. So this is it. Now I just need to plug it into this. You can either view it as a chain rule formula, or you can view it as the dot product formula. So that's it. So in this problem, dz dt will be del z del x. We got that. That's negative 3. And then dx dt, we got that. That's 4/5. Now del z del y, we got that. That's 1. And then dy dt, we got that. That's 3/5. So this is actually negative 12/5 plus 3/5. So I'm getting negative 9/5. And that actually does really match with our result from this picture right here. Negative 9/5 is that's almost negative 2. That is a really big slope, but going over 1 step means you go down 2 steps. That is a pretty big slope. So there's the process for how you do this. Usually, if you can just internalize this, it usually comes out pretty easy. What I'm going to do now is just present this solution in a little bit cleaner way. We did some unnecessary steps just so that we could kind of understand what's going on. But now let me just kind of write this in a little bit shorter symbols so that we can just jump straight to the answer. All right, these are the symbols that we use to represent these objects. D for derivative, U for the direction that you're moving in, F for the function that you're taking the derivative of, X naught, Y naught for the point that you're at. This is the derivative of F in the direction of U at X naught, Y naught. And this is the formula that we've been using to get the answer. It's just the chain rule, okay? And then we viewed this chain rule as a dot product. So if I wanted to clean this up, I can just write the gradient. That's we also read that symbol del. That's just this vector of partial derivatives. God, why can't I write a triangle? The gradient of f dot product with now this dx dt dy dt, we did that up here. All that turns out to be because u is the direction that you're moving in. We can kind of skip this step, right? U is the direction that you're moving in. So then when you parameterize the line, u hat ends up as these coefficients. And then when you take the derivative, all this stuff just goes away. So you just end up with u hat again. So all you need to do is make a vector that has these partial derivatives in it, and then dot product that with u hat, and then plug in the point x naught, y naught. Sometimes you'll see this like vertical line notation. When they write a vertical line after something, that just means you're going to plug in the point x naught, y naught. And that's actually all that we did up here, right? I found these partial derivatives. I plugged into the point to those partial derivatives, and then I did the dot product with u hat. So here it is, the derivative in the direction of u hat of f at x naught, y. Why don't I clean this? That's not going to give myself enough room. The derivative in the direction of u hat of f at x naught, y naught, y naught is equal to, what you do is find a vector where the partial derivatives are, the partial x derivative goes in the x coordinate, the partial y derivative goes in the y coordinate. You plug that point in, and then you just do the dot product with the direction that you're trying to move in, and it will tell you how much is the surface going up or down. The next thing for us to do is to really dive into this object right here, the gradient of a function. It's really an awesome thing. It's a really awesome tool, and it's going to be with us for the rest of this class. So, stay tuned.